Hello guys, and welcome back to Tichita. In the last lecture we reviewed the integrating factor, so today we're going to continue on that and look at more examples, and then hopefully we can close up this section. Alright, so first example. We know that x to the power of alpha, y to the power of beta is the integrating factor for below equation. The question is, what is alpha plus beta? So the equation is x squared plus xy squared y prime minus 3xy plus 2y cubed equal to 0. So let's open this y prime, which is dy over dx, and then we can end up with x to the power of alpha, y to the power of beta, 2y cubed minus 3xy dx plus x to the power of alpha, y to the power of beta, x squared plus xy squared dy equal to 0. So from here, dp over dy is equal to 2 beta plus 3 x to the power of alpha, y to the power of beta plus 2 minus 3 beta plus 1 x to the power of alpha plus 1 y to the power of beta. And at the same time we have dq to the power of dq over dx is equal to alpha plus 2 x to the power of alpha plus 1 y to the power of beta plus alpha plus 1 x to the power of alpha y to the power of beta plus 2. Now from here we know the equation should be exact, which means we are looking at these two, we want to see that these two are equal and these two are equal. So if we continue, we're gonna have 2 beta plus 3 is equal to alpha plus 1. As you can see here, so 2 beta plus 3 is equal to alpha plus 1. And similarly, we're gonna have minus 3 beta plus 1 is equal to alpha plus 2. If we solve this linear system of equations, alpha is equal to 1, beta is equal to minus 2, and alpha plus beta would be equal to minus 1. That's one example. Let's take a look at another example. So in this example, we're just looking to find the integrating factor. 2xy dx plus 4y plus 3 x squared dy is equal to 0. So similarly, we can write down dp over dy is equal to 2x, and dq over dx is equal to 6x. We're gonna minus, you can get minus 4x, and then we're gonna divide to minus p, which is minus 2xy, will end up with 2 over y. So therefore f is equal e to the power of fy dy, correct? So from here we can say f is equal to e to the power of 2 ln y or y squared. And then if we multiply this by the equation we have up top, we can end up with 2xy cubed dx plus 4y cubed plus 3x squared y squared dy equal to 0. And then from here we can define u is equal to x squared y cubed plus fy, and then we can write down 3x squared y squared plus f prime y is equal to 4 y cubed plus 3x squared y squared. So you need to refer back to lecture number 6 and 7 to remember how we're solving this right now. So from here, fy is equal to y4, and therefore x squared y cubed plus y4 is equal to a constant. So that's a complete solution to this problem. Let's take a look at another example. Again, we're looking to find the integrating factor. This time we are looking at 2 sine y squared dx plus xy cosine y squared dy equal to 0. From here, dp over dy is equal to 4y cosine y, and dq over dx is equal to y cosine y squared, again minus them. You're gonna end at 3y cosine y squared. Let's say what we can divide by. We can divide by xy cosine y squared, which we're gonna get 3 over x, which is a function of x. Therefore f would be e to the power of integral of fx dx, which is easy e to the power of 3 ln x. Therefore x cubed is our integrating factor. Let's take a look at another example. Remember guys, this course is all about solving different examples and then getting used to how to solve a specific form. 2xy minus e to the power of minus 2y dx equal to 0. Again, dp over dy is equal to 1 dq over dx is equal to y, and therefore minus 1 minus 2y, we're gonna divide this by exactly minus y, right? And then this is an f of y. Perfect. So therefore f would be equal to e to the power of fy dy. So from here we can say fy is equal to 2 minus 1 over y, and therefore integral of fy dy is equal to 2y minus ln y, and from here f is equal to e to the power of 2y minus ln y, or e to the power of 2y over y. We're going to continue with one more example. This time we're going to say dx plus 2xy dy is equal to y e to the power of minus y squared dy. So we're going to take this to the other side and clean this up. But at the very end, dp over dy equal to 0 because it's only dx, and then dq over dx is equal to 2y. So if I minus them, I'm gonna end up with minus 2y, and then I'll divide it by minus 1. This is 1 basically, so minus 1, so I'm gonna get 2y. It is fy, and integral of fy dy is simply y squared, so integrating factor e to the power of y squared. Next question, we're gonna say x to the power of alpha, y to the power of beta is integrating factor. Find alpha and beta. Okay, So the equation is y dx plus x 1 minus 3x squared y squared dy equal to 0. So we need to multiply this by both of these. So I'm gonna have x to the power of alpha, y to the power of beta plus 1, dx plus x to the power of alpha plus 1, y to the power of beta, 1 minus 3x squared y squared dy equal to 0. So dp over dy is equal to beta plus 1, x to the power of alpha, y to the power of beta, and then at the same time dq over dx is equal to alpha plus 1, x to the power of alpha, y to the power of beta, minus 3 alpha plus 3, x to the power of alpha plus 2, y to the power of beta plus 2. So from here you can see I don't have, so basically alpha plus 1 should be equal to beta plus 1. From here you can say alpha is equal to beta, but I don't have any other, I don't have this factorial here, so this is basically plus 0. That is gonna tell me that this is equal 0. So basically alpha is equal to minus 3, therefore beta is equal to minus 3 as well. That's how we're going to solve this equation. Let's take a look at a full example as our next example. Okay, we're gonna solve this equation. 1 plus y squared dx is equal to tan inverse y minus x dy, correct? So basically we want to take this to the other side and then simplify. We're gonna end up with dp over dy is equal to 2y, and dq over dx is equal 1. Again, minus 2 minus 1, and we're going to divide by minus 1 plus y squared to make this a function of y, and then integral of fy dy is gonna be tan inverse y minus ln of 1 plus y squared, and therefore f is equal e to the power of tan inverse y over 1 plus y squared. Now we can multiply this at top to both sides to make an exact equation, and we're gonna end up with e to the power of tan inverse y dx plus x minus tan inverse y multiplied by e to the power of tan inverse y, sorry, this is a plus, over 1 plus y squared dy equal to 0. To solve this, we know from before we need to create u is x e to the power of tan inverse y plus f of y, and then from here du over dy is equal to x 1 over 1 plus y squared e to the power of tan inverse y plus f prime of y, and then from here we find f of y to be the integral of minus tan inverse y over 1 plus y squared. I forgot here we have tan inverse y e to the power of tan inverse y dy. So if we solve this equation, then we can find the solution. So let's take a look at another example. We have y x squared minus y dx plus x squared plus 3y dy equal to 0. If we go as our regular dp over dy is equal to x squared minus 1 and dq over dx is equal to 3x squared, therefore the minus is minus 1 minus 2x squared, but neither p or q, if we divide it by, we will end up with a function of x or y, so we cannot use this integrating factor. So we're gonna try another. I'm gonna name this a. So in b we're gonna say, okay, I'll do x alpha y beta plus 1, or basically we're gonna try x alpha y beta. So therefore we're gonna have x alpha y beta plus 1 x squared minus y dx plus x alpha plus 1 y beta x squared plus 3y dy is equal to 0. And then from here we're gonna solve for alpha and beta. So dp over dy is equal to beta plus 1 y beta x alpha plus 2 minus beta plus 2 x alpha y beta plus 1. And then we're gonna do the same with q. We're gonna have dq over dx is equal to alpha plus 3 x alpha plus 2 y beta plus 3 alpha plus 1 x alpha y beta plus 1. So if you pay attention, this and this are equal, and also this and this is the same, meaning beta plus 1 and alpha plus 3 should be the same, and also minus beta plus 2 and 3 alpha plus 1 should be same. If we solve for this linear system of equations, we're going to end up alpha is equal to minus 7 over 4 and beta would be 1 over 4. This is another example where our regular dp over dy and dq over dx will not give us an answer. So that should be it for this lecture, and in the next lecture we're going to open up another type of equations and how to use integrating factors to make homogeneous functions and solve them. Thank you very much, and see you guys next time.